started a new one. You can see it now. But I'm gonna have to move because my phone's under there, so I have to move that one in. Okay.
Wait, I have a book. I have a notebook. Will notebook help it?
Yeah, probably. Or like even just get me a pen and that will work because I feel like that's gonna be too thick.
How we doing, everybody?
Hello.
So I am Professor McLean, and I assume that we're all here for a practical review for Bio 110 specifically, yes? Yes. And so what this is going to be, it's scheduled for 2 to 3. It's likely going to be more like 3:15, 3:20. I will try to move quickly, so if you have a question, you got to raise your hand and ask it quick so we can keep this moving. There's a lot of information to get through, and that becomes front and center to your challenge of the week here as we get ready for the practical, right? So just as an inspirational thing, it's not about how smart you are, it's about how much effort you're putting in. So please make sure you're blocking out enough time to get yourself the exposure with this material as many times as possible in order for you to have maximal success, right? So we started out just after the practical, and this practical here for the final will only be for the second half of the semester. It is not cumulative. So it's basically from axial skeleton forward, right? And so just to get us started, we've got the skeleton here. The axial skeleton is sitting there basically around the axis that you spin around on, right? Which is skull, spinal cord, ribs, or spine, I should say, ribs, is the axial skeleton versus the appendicular skeleton, which is doing your appendages, right? Including the large surface area bones that we're going to need to attach to big, powerful muscles that are going to run your limbs here as well. Which is why bones like the scapula are officially part of the appendicular skeleton, not the axial skeleton. I'll be touching the screen and doing that all day long. All right, so from there then, our main work here in the axial skeleton is the skull. So we've got these colored up skulls we had in lab for you. Understand that unless you've got the most naive or the nicest lab instructor, this is not the skull you'll be tested on. Instead, the skull you're tested on will look closer to that. So we use this just to make it easy for me to point out things to you, especially in the back of the room from where I'm at up here. But you learn them like this, but then you must transfer them to this in order to actually get the points, because this is the one you're going to be tested with, right? For today, I'm using the colors. That way I can get the whole room involved, right? So your frontal bone is the first one, and that's right up here in your frontal area, just above the frontal lobe of your brain. This is your forehead, right? And so that's this purple guy right there. And it says straight up definitions, yes? And locations. So there's your frontal bone. Now, just inside the frontal bone, you've got this space. And one of the models I forgot to ask for was the sinus model, but we've got a frontal sinus right there in that frontal space. And let's see how far away I can get from the screen. So here's your frontal sinus. There is how that works here. I'm also going to try to use my pointer, which doesn't work on the screen. In there, that's the purple. And in our model of the sinuses, you should have this one under your belt as well. It's the yellow right here. Frontal sinus for your frontal bone. Questions so far? All right, so we keep the terminology easy to begin with. Then we get the temporal bone, and that's this bone up here, basically over your ear. Your temporal bone holds your acoustic meatus, which is the hole that your ear is going to actually make, right? And that is also going to be holding on to a zygomatic arch right there, which will become the back part of your cheekbone. So it's the side of your skull down to about your ears, which is your temporal bone. And this is too far, so I'm going to stick myself right up here in the corner. With the temporal bone, if we open up the skull, we can see that the bone here is very, very thick on the inside. That's called the stony region, or the petrous region. And so, like petrified, right? And so in here, this is where all of your balance and your hearing structures are. Your cochlea, your semicircular canals that you'll learn about in 111 next semester. And so it's just a bunch of tunnels kind of carved out into this thick bone. So all of the structures of your balance and your hearing are also embedded in the temporal bone right here, the petrous region. As far as a sinus that can be associated with this, this is these purple guys next to your ears called the mastoid sinus. Then we've got Your parietal bone. Now your temporal bone is down here by the ears. Your parietal bone is the top of the sides of your head on either side, right? And there's not a whole lot to be said about these guys, with the exception of this line that you see, the suture that holds onto your two parietal bones, and how it interfaces with this brown bone, which is called your occipital bone, for over your occipital lobe. That's where you see in your brain. See how this kind of looks like a Mercedes symbol? That is the Greek letter lambda. And so as a consequence, this particular suture is called the lambdoid suture. And it's one of the sutures that you're supposed to know for the axial skeleton lab. Questions there? All right, so parietal bone. Right over the parietal lobe of your brain. Then we've got the occipital bone. That's this guy down here, the brown we just talked about. This is over the occipital lobe of your brain. I hope you know at this point, but if you don't, you will by the middle of next semester, that your eyeballs take in the light, but you don't see anything until it hits it back here, which is why getting hit in the head with the back of the head with a baseball bat or a pitch can lead to blindness. See The Sandlot if you've ever seen the movie, right? It's also why we've got the batter's helmet here. It's simply so it's not to protect your ear. Yeah, it hurts, but oh well. It's to protect the back of your head here, because if you get hit with a fastball in the back of the head, next step, blindness is a risk. So that's why they've got that big protective thing. And that's simply because the occipital lobe, occus meaning eye, just underneath the occipital bone here. With the occipital bone, we've got the hole that your brain is going to meet your spinal cord with. That's called the really big hole, and that's the foramen magnum. And if you look at what those terms actually mean, it pretty much means really big hole. And your spinal cord comes out that foramen magnum right here. We've also got these occipital condyles here, and this is what the atlas bone, that C1 vertebrae, is going to hold on to your head with. And the action of that C1 vertebrae on those occipital condyles here is going to give you the yes motion. So your first cervical vertebrae allows you to nod yes. And then if you remember, we'll get into this, but your second cervical vertebrae, the axis, is what allows you to go no. And it's simply because that smooth part there provides a nice, shiny surface with low friction. Questions? All right. Then we start to get into the more of the internal bones. Your sphenoid bone has these wings, and it's here, this green we see. And you're not going to really see this very well unless you open up the skull. But what this is going to do is set up the base for things like your pituitary gland of your brain. And so one of the bone markings here in the sphenoid bone, this wing bone, is this piece right here called the Turk's saddle. Because it kind of looks like a saddle if you've ever ridden horses. And the person that's riding it is your pituitary gland. And so this is how we set up the connection between your nervous control and your hormonal control. And we actually give that hanging pituitary you learned about in the brain lab, or you will if you haven't gotten there yet. It sits right there in the sella turcica, which is your major bone feature of the sphenoid bone. Questions there? We've got these greater wings and lesser wings, but really it's just recognize the wings, and you'll be able to know what that is. Now, sella turcica. Yep, the location of the pituitary gland. Now, as far as a sinus that can be taken with the sphenoid bone, we do have the sphenoid sinus, and that's this blue guy all the way toward deepest part of your face, right in there. Sphenoid sinus. One of the most common confusions of answers that I've seen on these practicals over the several campuses I've taught this at is the confusion between the sphenoid bone and the ethmoid bone. I think it's just because your mouth has to do the same basic stuff to get the sounds out, but keep them straight. The ethmoid bone is this brown bone right there, and it's basically a rod of bone that runs right down the middle of your skull versus this wing type thing of the sphenoid bone. We do have two different bone markings of importance on this very central, tinier ethmoid bone. It's this yellow one right here. And what you can see if you take a good look at these skulls with that ethmoid bone, there's a ridge that runs right up the middle of that sucker. That ridge is called the crista galli. And what the crista galli does is it grabs onto the membrane that's holding onto your brain, and it anchors your brain in place. In fact, this is one of the very few places your brain is actually held in place which is why concussions are a thing. Right? It's just these membranes that are holding your brain inside of an ocean of liquid, but when you stop, well, inertia is a thing. Your brain keeps going forward, and because those membranes tying here to the crista galli are flexible, your brain has the space to kind of come in and punch the front of your skull equals concussion. Yeah? Crista galli. The other thing we've got here, in the brain just north of this, as you say, just superior to this, are the olfactory bulbs that you smell with. And so those olfactory bulbs are sending down bare nerve endings through the cribriform plate. That's all these dots that you can see on either side of that crista galli right down the middle. That's for your smell neurons. In fact, this is one of the very few places in your body where bare neurons are just out in the environment. We coat them with the mucus of the inside of your nasal passages, and their job is to hold on to all the 45,000 different smells that we can smell and send that smell information up through this cribriform plate to the olfactory bulbs, which contain your smell maps. Questions on sphenoid versus ethmoid bone? All right. Then in the ethmoid bone, really where you're going to be able to see it is this yellow here. Not the pink in front, that's a different one. We'll talk about that in a second. It's the yellow as you take this person's eyeball out and look at it from the side. Kind of dark. Well, you could also cut their head in half and look at it from the top. All right, as far as the ethmoid sinus goes, that guy is in green here. Then we get into the mandible. Mandible is functionally your jawbone, right? And with that, we've got the body of your mandible, this mandibular ramus, which is just a flat projection, and a mandibular condyle, which kind of sits up right here in the temporal bone, just in front of your acoustic meatus there. For those of you who have ever suffered from TMJ, this is the issue right there. That articulation does not do very well, so your jaw gets locked shut or it gets locked open. It's a real fun thing to eat a cheeseburger with this if you've ever had it. And this is a thing that a lot of times will fix itself with age as your skull gets more proportional. But that condyle is the point of articulation for your jawbone or mandible with the rest of your skull. Right? Then we've got the coronoid process up front, which kind of sets this up to fit inside your zygomatic arch and kind of keep things lined up appropriately as you go up and down with your chewing and talking. Questions here on the mandible? All right. That goes hand in hand with your upper jaw. That's the maxilla. Purple on the screen, orange here on my model there. And that's just your upper jaw. With the mandible comes the hard palate, or the palatine process, right? And if you run your tongue up the top of your mouth, you can feel hard in front and soft in back. Well, that's the hard stuff is actually your mandible you're feeling right in front. And in the back, it kind of opens up a little bit to give you the soft palate, which you can see as a consequence here and here, those holes. Their maxillary sinus, this last one, that's shown in pink here. Then we start getting into the detail bones of your skull. I hope nobody gets this one wrong, but nasal bone is here. Not down in the floppy part. If you're going to break your nose, it's got to be up in here, right? And so, nasal bone. The zygomatic bone is your cheekbone. It's this. It sets up the outer lower third of your orbit here. It meets up with your zygomatic bone, and collectively we've got your zygomatic arch here. But if you've got high cheekbones, you've got high zygomatic bones is really what you've got here. And that articulates with your maxilla in front, your temporal bone in the back as well. Now when you cry, which nobody's going to do after this test, I'm sure. But there's a point to this story. When you cry, what you've got is a lacrimal gland. And the gland itself for your tears is up here in the upper outer corner of your eye. And how this system works is this sends the tears down over your eyeball. It washes across your eyeball to the lower middle corner. And then you've got that pipe down here. That's called the lacrimal duct. And I'm sure you've cleaned Mr. Sandman out of your eyes in the morning. And the reason why it's always in this corner is because that's the direction of tear flow. And throughout the night, all the garbage your eye collected gets washed into the drain. And it doesn't go down the drain, it just collects on top. You clean it out in the morning and you're good to go. When you cry, you probably have noticed that you have to blow your nose a lot. Because there's a duct right there and it just goes straight down into your nasal cavity. So after you're done crying, it's not that you actually made more snot. What you're blowing out of your nose is the tears that didn't spill over the side but went down the lacrimal duct. This bone, the lacrimal bone, is named after that lacrimal duct. And so it's basically exactly where we would clean Mr. Sandman out. In this case, it's the pink bone just inside the orbit. Does that make sense? Any questions so far? All right. Now we start to get into some of the real detailed parts. In the back is the easiest place to see this guy. You can see the inferior nasal conchae or turbinates here through the actual nasal opening, but it's easier to see back here. It's the green. And what's going on here, if you were to give yourself a cross section, all of your nasal conchae, which is basically the nasal snail, the turbinates like a fan, what's happening is you're breathing in and the air circulation is set up. Let's see if I've got a better picture. I do not. The air circulation is set up to actually spin. And so when you're breathing in through the nose and out through the mouth, that breathe in through the nose is doing a couple of things for you. It's spinning the air before it allows it down in the lungs, and all this is surrounded by mucous membranes, sticky stuff. So when we spin it, what happens is all of the spores, the bacteria, the dust, the garbage, a good proportion of it gets spun out into that sticky stuff. It sticks. You know, boogers are sticky for a reason. This is the reason. And now your air that you're breathing down into your lungs is cleaner. It's also going to pick up some of the moisture from those membranes as it spins around and give your lungs a break as far as the drying action of the air. That's why they're called turbinates, because it's spinning the air, kind of like a turbine, or conchae for the spiral shell of a conch. Make sense? All right, so that one. Also in here, we've got the nasal septum, which is part membrane, part bone. The vomer bone straight up the middle of your nose. In this case, this is gray sucker right there, sets up the left-right separation between your two nasal passages to get up into those nasal turbinates. Questions there? All right. Now we get these sutures of your skull. We've already talked about the lambdoid suture, right? We've also got a suture that if we were to cut right down it, we would get a mid-sagittal section, yes? And so we call this between your parietal bones, that's your sagittal suture. We've also got the between your parietal bones, I should show it here, and your frontal bone. That's called your coronal suture, because if we cut this way, it would give you a coronal section, yes? And then down between your parietal and temporal bones, we give you the flat suture or the squamous suture, which is that. Not sure why it's called the flat suture, probably because it's as close to flat as we've got. And so those are the different joints between these very much immovable bones. Questions on the skull? Beauty. So we're moving this along. We have in your axial skeleton one bone that is not attached to anybody else. And there it is right there. I can't take the skull off and I can't pull the thing up. But if you look down in here, we've got this bone. That's called the hyoid bone. It's the only bone in your body that doesn't articulate with any other bones. And the whole point of that hyoid bone right here is to help you speak. Your tongue, your muscles, they all use that hyoid bone as an intermediate in order to turn some corners in your neck that would otherwise be too complex for us to get this job done. So a muscle pulls on the bone, which then pulls on something that then pulls on the next thing, and that's how we actually get swallowing and speech happening. And that's what the hyoid bone is for, right? The only bone that's only attached by anything by soft tissue. Then we get into the spine. And your spine has several sections, yes? And it just has to do with what they're innervating. So your cervical spine is your first 7 vertebrae. So it goes C1 to C7. And if you count them up, you've got 1, 2, 3, 4, 5, 6, 7. And you can run this down the back of your neck and you can feel that very first prominent vertebrae as you're moving down. That prominent vertebrae that you feel is called the vertebra prominens. And it marks the official anatomical end to your neck. That's C7. Once we get further than that, we've got 12 thoracic vertebrae that interlock with each other pretty significantly. In the thoracic vertebrae, if you look at them from the side, they look like giraffes. A giraffe's head. And that long giraffe's head, what that's going to do is going to interlock with the transverse processes of the vertebrae below it. And if you try to actually do any flexibility of this part of your body, you're going to find it doesn't happen. And the reason it doesn't happen is because that giraffe's face of your next 12 vertebrae, the thoracic vertebrae, interlock with these sideways transverse processes, and it restricts the motion. Why? You've got a breathing apparatus in here that must always be open. It works by vacuum. If we twist you there, you stop breathing and die. You've also got a heart in there that needs the space to work. And so we restrict your motion in your thoracic region simply to allow the wide open thoracic cage to stay that way. Does this make sense? All right, now from there, we've got your lumbar vertebrae. Your lumbar vertebrae are very big in the body because they have to hold up all the weight of everything north of that, right? Lumbar vertebrae is basically the workhorse of your back. And this is the reason why if you get into your late 40s and 50s without back problems, congratulations, you're in the minority and you're winning life right now. Because these guys take all of the weight that's above them. And if you're busy doing things like lifting with your back, well, this is the area of most concern, right? And so your lumbar vertebrae, there's only 5 of them. They are very large in the body because they've got to basically support your weight without compressing. But we also get a lot more flexibility here. This is where our flexibility is. And if you look at the profile of a lumbar vertebrae, they look like the face of a moose. And that moose's face, a little bit blunter, quite less protrusive, that doesn't lock in with the transverse vertebrae as well. The transverse processes of the lower vertebrae as well, which means we get quite a bit more flexibility from the lumbar region. So if you've ever done the kettlebell thing, that's where we're working. Questions here? Now, the biggest workhorse of your spine has actually been forced to work so hard, it stopped being individual vertebrae. And it just took the lower 5 vertebrae you had and fused them all together into the sacrum, which is actually several vertebrae all fused together. Why would we fuse them? So we could fuse them in with your hips as a bipedal adaptation, right? 2-legged adaptation, and support all of the weight from the hips up. And we needed that extra fusion and size there as we moved to bipedalism, and we were counting on our back to hold all this stuff up, right? And then at the very last, we've got a tail. Many people are born with tails. Unless you're mom or dad, you likely won't know it, because the first thing the doctor is going to say is, you want your kid to have a tail? Mom and dad typically say no, and they say, okay, we'll be right back. They go chop it off, and it's done. Right? We all have tails. Sometimes people get born with the tail sticking out. Most of the time, not. Right? And so that's your last 4 fused vertebrae. We lost our tail as we lost the need to balance ourselves. As we got kicked out of the forest and forced into the grasslands, that tail became less of a balance and keep us in the trees in survival, and became more of a handle for predators to grab us with. And so we just lost it. So this is one of these vestigial organs that we still retain because it's not killing anybody. But if you've ever broken your tailbone, you understand how much that hurts and how you wish somebody might have killed you then. All right? So that's your spine. Questions here?
So what's the name of the tailbone?
Tailbone is the coccyx. All right, so with the individual vertebrae, with your cervical vertebrae in the neck, they have, yeah, go ahead. I am, just not, yep. All right, so with your cervical vertebrae in general, listen guys, what you need to do to separate these is just understand the basics of some things that need to happen in each part of the back. The first one is that you've got vertebral arteries that start here and need to feed your brain. This is the only place on your back where you need vertebral artery space, because it starts at your shoulders and it feeds your brain. It doesn't go down, it goes up. And so only your cervical vertebrae will have these holes on either side. The transverse foramen. And that's for these vertebral arteries. Further south of your neck, those holes don't exist. So if you don't see those holes, it's not cervical. If you see those holes, that's a neck vertebrae. And then it's just a matter of, is it one of the special ones? So that's the easiest way. The other thing you're going to notice here, you got plenty of flexibility in your neck, and that's because these transverse processes, there's nothing locking into place with next vertebrae, like in your thoracic or lumbar section. Your atlas is the first because Atlas holds up the world, right? Greek mythology. Your axis is what you turn around on. That's your C2, to answer your question, yeah? And so with that atlas, what you've got are very, very non-pronounced vertebral foramen. Transverse foramen, although they're there. You've got almost no spinous process there. And what this is, and a very nice, smooth part of these condyles here. And what this is going to do is your occipital bone is going to sit right on top of atlas. This matches with the occipital condyles we saw around the foramen magnum, and you do this. The axis is the C2 vertebrae. And the really important thing about, what the heck just happened? The really important thing about the axis is this process right there. It's called the toothy process, or the odontoid process, because it looks like a little tooth sticking up. What's going to happen is you've got muscles that are going to grab here and then come out to the side of your shoulder. And so when I contract this side of my shoulder, what happens is this muscle pulls on that odontoid process, and then my whole head goes this way. And if I squeeze this side, it's going to pull on that odontoid process, my head goes that way. And so the entire no motion you've got is completely dependent on that one extra process that's coming up there. And that's your axis. So because you're spinning around your axis. All of the other cervical vertebrae, they're a little different, but really you're just looking for that transverse foramen for your vertebral artery, and you know it's a cervical vertebrae. Then you've got your thoracic vertebrae. Hey, check out the giraffe. Do you see it? That's it. And that's why you've got no flexibility here. They lock into these transverse processes under the side and restrict your ability to move. That's on purpose, right? And then from there, notice no transverse foramen here. And functionally with your thoracic vertebrae, the one thing you're going to articulate with are other vertebrae and your rib cage. Now with your lumbar vertebrae, you see the moose? Can you see that face? I don't know how many people spend time north, but trust me, that's what a moose face profile looks like. And what you're getting is less interlocking with the other vertebrae around, which is going to give you the extra flexibility you have of your lumbar region. Yes? Make sense? Also, no transverse process, no vertebral arteries here. On a really big, thick body to support all that compression weight of everything it's carrying above it. Then you've got your sacrum, your 5 fused vertebrae. And that's basically the rest of everything is going to sit in that sacral canal. And then at the end, you've got your tailbone. That tailbone becomes really popular as the weather turns to like this. And we start seeing sheet ice in parking lots. Because the move is, right? So what happens is, look, there's nothing solid around this. It's just the tissue of your butt. And when you land like that, there's nothing to support it, and it's just kind of protruding out, it snaps. And there's a lot of nerve endings in this area, so all that inflammation and irritation can cause some real pain. And it's so much pain that like they give you a rubberized toilet seat to bring around and sit on for the next couple of weeks. That way you have some chance to heal. True story, the drummer in my old band busted his tailbone like this for the next 3 months. Every gig he had 2 of these so he could keep drumming for it. All right. Now, also with this is the sternum. The sternum is a point of attachment for the muscles on top. Yes, it's protected. Yes, these ribs are protected. But really, the sternum here, this flat bone, is so your pectoralis major muscles can bind and you can get some limb movement on top of this system. We've got the body, which is the main part. We've got the manubrium, which is what your clavicles are going to come in and articulate against. And down here, we've got the xiphoid process, a nice, beautifully engineered spear point right next to your heart and lungs, which this becomes a problem, right? Especially for goalies in lacrosse and hockey. And that's one of the reasons why they wear that big thing on their chest, is to avoid that being broken and jamming up into your diaphragm, heart, and lungs. Right, so that xiphoid process is necessary. What it's doing is hooking up your rectus abdominis muscles to your pubis. And so when you're doing a sit-up, what's happening is your xiphoid process is pulling the top half of your body towards your pelvis by way of its connection to the lower inferior part of your ribs and that xiphoid process there. It's also a point of connection for your diaphragm, which you're going to need to breathe. So it's an engineering flaw, but that flaw has its advantages. Yes? Questions? Okay. The first 7 ribs are your true ribs. So named because they have an articulation of the spine in the back and their own articulation in front on the sternum. Once you get ribs 8 through 12, those ribs are all connected as a group, or they're not connected at all. So that's why we call these the false ribs. They're just as legitimate acting as ribs as your true ribs. It's just a matter of attachment, right? These last 2 ribs right here, your floating ribs, they're not attached to anything. These are your most commonly broken ribs. For those of you into plastic surgery and the whole Hollywood wasp waist look, these floating ribs are the ones people get removed to give you the extreme hourglass shape, if that's something that you're looking for. I feel like it's kind of ridiculous. However, they are there for a point, right? But some people decide that those need to go, and they get them taken out. So that's the story with the ribs, and that's your axial skeleton. Questions there, guys? All right, so from there, we move into your appendicular skeleton, getting the appendages to move. And so one of the key features of getting your limbs to move is the muscles closest to your torso need to have a whole lot of size. That way you get the power. But if we don't have a whole lot of surface area on the bones to attach them to it, you're not going to get that size or power. So we start here with the scapula, and if you notice that scapula has a lot of nice surface area on it. We're going to get your infraspinatus muscle down here underneath, your supraspinatus muscle up here on the top, part of your rotator cuff right. If you're not in my section of the lab, you don't need to know that, but if you are in my sections of the lab, pay attention. And now what winds up happening is we have a whole lot of stuff, these muscles, to give us the power we need coming out of the upper limb. Now, from there, your scapula. This is the spine of your scapula. We got this nice body here. And then we've got the glenoid process, the acromial process, the coracoid process, and the glenoid cavity, which is going to give us your actual shoulder. And you can feel that here. You can actually, your scapula starts back here, but it actually ends up here in the front of your shoulder, and that's what your clavicle, your collarbone, is actually coming up and touching against, this acromial process. That's why this is called the acromial region of your body, from this process right there. Yes? Now, one of the things that you're going to need to do is know left versus right and a disarticulated skeleton. Well, this sounds like it should be a really tough project, but to be perfectly honest, it's not. What you're going to need to understand is two things. The first is you're going to attach your muscles around the spine. This here, that spine, part of it is to attach the muscles, and the muscles fill that in. And the muscles fill this part in. So when you're actually looking at the model, it just looks like muscle, white line muscle, right? So that needs to face out. This flat piece, that goes up against the rib cage. And so the first step is just which is going deep, which is going superficial. And if you look at this, it makes quite a bit of sense why that would be that way. Because if you try to put that spine in, it's just going to get in the way. So we need the spine facing out. We also need this glenoid cavity to face lateral, not medial. The challenge here is we're just going to put the bone on. And you can't touch anything, right? So you've got to be able to look at a thing and kind of like organize your body in such a way where it makes sense. And then this is how if I see people spinning around on this practical, I know they're winning. Because that means they've actually got it, right? And so spine out, glenoid cavity, lateral, and this, therefore, is a right scapula. And that's the easiest way to come up with this. Don't make this too complicated. Come up with 2 or 3 important rules, memorize those, leave all the detail behind. We've got too much other crap to know, yeah? And so scapula. Questions here? All right. And that's everything we said. The clavicle, you don't need to know left versus right. You just need to be able to understand that this is your collarbone. You should also be able to do this. This articulated is just this S-looking bone. It's the only S-looking bone we got. Left versus right is not a thing in any of the sections to my knowledge, so just understand clavicle is here. It articulates with your scapula and with the manubrium of your sternum. Then we've got the humerus, your upper arm bone. There we go. And this is another one of those left versus right suckers, so let's take this out and take a good look at it. We're also going to need an olecranon process. All right, so this is the olecranon region of your body, right? Your elbow. And what we need to understand is it's called the olecranon because we've got an olecranon process of your ulna. And so your elbow feels like it's part of your upper arm, but really your elbow is part of your forearm. It's that piece right there. That is your elbow. You see this? And in order to get left versus right on this sucker, what we really need to do is understand how your elbow forms. Well, it forms at the joint. It's a hinge joint. It articulates with your humerus. Now, this humerus has two basic sides. It's got a side with a basin in the back, in the center. That's called the olecranon fossa. And then it's got a side that's really smooth and round on the front. That's called the trochlea and the capitulum. And what's going to happen is this olecranon process in the back is going to wrap around that trochlea and capitulum in front, and the olecranon process will fit into the olecranon fossa and give you a straight up hinge joint. See how that works? Now notice, the elbow points backwards, right? And so if we're going to figure out left versus right with a humerus, what you need to do is put the olecranon fossa pointing backwards. We've also got a very smooth port right here for articulation. Anytime you see something super smooth, that's been ground down or evolved to be smooth so we reduce friction. That means we're going to be articulating there. And so we've got the head of the humerus pointing medial. We've got the olecranon fossa, the space in the center, pointing backwards or dorsal, and therefore this guy is a right humerus. The other way you could look at this is you could say, all right, head facing medial, and the capitulum, the rounded articular surface, facing forward. And in that case, you're going to get the same basic answer. In this case, my capitulum is facing forward, head facing inside, so this bone I'm holding is a left humerus. Questions? Okay. And again, keep your rules simple as you're studying this stuff. There's a lot of stuff to remember. Don't confuse yourself on purpose. Radius and ulna, we do not need to know left versus right, or to my knowledge, as individual bones, but you just need to know that these are your forearm bones. You also need to know that radius is the thumb side, ulna is the pinky side. And after that, you're good to go. Questions there? All right. And with your bones of the hand, your bones themselves, these guys are called phalanges. Then you've got the hand bones proper here. Those are your metacarpals. And then you've got your short wrist bones back here. Those are your carpals. And how the radius and ulna work is they've got these malia on either side, these little protrusions that stick up on the left and right. Your carpals sit down in between those protrusions and are literally trapped there. We tie you down with some ligaments, and now your wrist cannot fall off the edge of your hand because there's literally little speed bumps on either side holding them there by the carpals. Make sense? All right, so the big mistake people make here is to confuse carpals of the wrist with tarsals of the ankle. They're the same system, same basic setup, but the names are different, and you will lose the points if you mislabel, yes? So just keep these guys straight. Wrists are carpals. As we move south, we've got the os coxae, which are your hip bones. This literally means, os coxae literally means bones of the hip. And we're some of the few creatures who have these fused like this. So we've got an ilium, which is a massive place of surface area for the largest muscles you've got in your body, for the most power you've got in your body, right? This is why you've got that power. Lots of surface area for lots of muscle fibers to attach to. We're thinking gluteus maximus attachment and other muscles like this, yes? Knowing left versus right becomes a thing, and so we've got the ilium up top. We've got the ischium at the bottom. The ischium is what you're sitting on right now. And about 40 minutes into the lesson, you can probably start to feel the soft tissue between that ischium and the chair start to bother you a little bit, right? And that's because you've got maybe a half an inch worth of soft tissue between literally a rock and a hard place, yes? So what we've got is a ball and socket joint. This is called the acetabellum. And that ball and socket joint needs to face lateral. The other thing that needs to happen is this sciatic notch needs to face dorsal, back, right? And this nice, beautiful surface area here that's smooth on that side needs to point lateral. You see how we've got this rough side here on your ilium, but a much smoother side there? This rough side here is so we can articulate with a sacrum, like so. The smooth side, you don't get the same articulation. So that rough side's going to be pointed medial. Acetabellum's going to be pointed lateral. This smooth spot is going to be out. And so this is a right os coxae, our bone of the hip. Questions here? For my guys, you need to know not left versus right of the hip, but you need to know male versus female. Remember about the orientation of the ilium, how a male is going to be much more up and down, how a female is going to be flared to the side, how the canal formed by these three bones is going to be much narrower in a male, much wider and round in a female, and how in a male we're going to see a curved sacrum and coccyx versus a female is going to be much flatter, opening up that birth canal so you might actually get a baby through it. Male versus female in my sections, left versus right in everybody else. Questions? All right. Your femur. Largest bone of your body, hardest to break. What we've got here is femur. Obviously, the head is going to be pointing into the acetabellum of the hip. That's your ball and socket joint. So that sucker got to be pointed medial. And then it's just a matter of understanding how the tibia of your lower leg articulates here at the knee, because this could make some confusion, right? Now, we've got a notch in here in the center, and we've got a much deeper notch in the center on this side. But understand how the tibia is going to work here. I've got my tibia. That's all right. No, I don't. There it is. If we've got your tibia, what you're going to do is you're going to see these condyles there and these guys here. And how this works is we kick like this. Yes? So if you look, this smooth surface, this condylar surface, kind of rolls up the back. It doesn't roll up this side at all. It rolls all the way up here. And this is so you have a nice smooth surface so you can do the move, right? That's this. And so if that's the case, then what we need to do is we need to put the head medial and we need to put these condyles back. And in this case, a right femur. Very simple, easy to remember rules here. Don't get lost in the details. Questions? Okay. Next winds up being your tibia and your fibula. Your tibia is another one of these that you need to know left versus right. So this becomes an easy project if you understand how the tarsals of your ankles kind of lock into the lower leg. And it really becomes, okay, you just need to understand that this surface is superior, that surface points down, and from there, in your tibia, what we have is a medial malleolus. That's this piece here. What's going to happen is the tarsals, your ankle bones, are going to get trapped between the medial malleolus of your tibia and the lateral malleolus of your fibula. Together, they pinch in, and now that's not going anywhere left versus right. In fact, what we've done is we've made a nice anchor point so we can pinch the talus right there. That's your hinge. And so the malleolus, medial on the tibia, lateral on the fibula, trap that talus and allow you the hinge action of your ankle here. And that's how you're going to tell left versus right of the tibia. You put this guy superior and you figure out, okay, I've got this guy. You've got a curvature in front and kind of a convex thing in the back. And so you look up top here, you can see how this is almost like a kidney. The outer part of that kidney, the smoother part, goes forward. This is where your kneecap goes. Once you get front facing, then it's just a matter of where is this malleus. It is always medial. And so in this case, what I'm holding is a left tibia. Questions there? Okay. Next. Bones of the foot are the bones of the foot. We're not going to get too crazy on this. We've got the talus, which is what's being trapped by the malleoli of your lower leg. We've got the calcaneus, which is functionally your heel. That heel is going to get attached to a calcaneal tendon, also called the Achilles tendon, which hooks up with your gastrocnemius and your soleus muscle, so we can actually use that hinge to do this, right? Heel is calcaneus. Otherwise, we've got the rest of your tarsals here, and then your bones proper in the front, and then you've got your phalanges, just like up in your fingers. Not doing too bad. We're already in the muscles. All right. I'm just going to breathe for one moment and take some coffee. And then we're going to get back to it. The joints. I don't have the joints in here. Guys, just understand that this is not a complete exhaustive list of everything. We have the types of joints. We've got the synovial joints, right? That is also going to be something that you need to know. We're not going over it just for time. We're already running like 20 minutes, half an hour over time by the time we're out of here. So that's it for the skeleton, but understand there are going to be some stuff that we just didn't have a chance to cover today, right? Okay, so as we get into this, one of the whole points of your skeleton is to allow your movement, and so they become the anchor upon which your muscles get to squeeze. And there's just a couple of different ways we can attach muscles. We can attach them directly, epimysium to periosteum, or we can use little ropes or sheets to kind of make that attachment indirect. The ropes would be tendons. The sheets would be aponeuroses, like you see here with your rectus abdominis, hooking up your xiphoid process down to the pubis of your pelvis, right? And it's a flat sheet instead of a rope. But it's the same basic thing, indirect attachments. Now for every muscle, these are linear structures, right? They attach from point A to point B, and the only thing muscles can do is squeeze. And so because these guys are ropes, basically, with a squeezy ability, where we attach them matters. Because they're only going to be able to squeeze, and if they're attached in the wrong spot, then the motion becomes wrong. Well, the attachment point here is always going to be causing some version of motion. And you notice as I'm moving my body, what happens is, in relation to a particular joint, one side of that joint stays relatively still, and the other side of that joint is moving quite a bit. In these muscle attachments, the side of the muscle attachment that's not moving, that's called the origin. In general, it's closer to the midline of your body, but not always, right? And next, we've got the insertion, which is what's giving us the moving. So we're going to squeeze against the origin so we can pull the insertion closer to us. And that's it. That's it. All the muscles can do. They can squeeze and they can not squeeze, and we use gravity or other things, opposing muscles, to pull this guy back. As we get into the muscles of the head, the frontal lobe is covered by the frontal bone in the frontal region of your body, and right up front we've got the frontalis muscle. So if you're screwing up forehead stuff, guys, I pity you, because it's all frontal stuff, right? Anything here, just some version of frontal. And frontalis is this motion. Unless your eyebrows. That's all. That frontalis can be considered as its own muscle. It can also be considered as part of a larger muscle called the epicranius, which also includes back here the occipitalis over your occipital bone, right? But you can call it the frontal belly, the occipital belly of the epicranius, or you can call it frontalis or occipitalis. I'm not sure which way your lab instructor decided to go with this. They're synonyms. And so the other bone we've got, if you can wiggle your ears a little bit, I can with incredible focus. I've been practicing. So. All right, that's your temporalis muscle. All right, and some people can really get it going. Other people got nothing. And that's a genetic thing. All right, and then as we move forward, we've got your crushing muscles for your jaw. That's your masseter muscle back here. Hooks up to your zygomatic arch and then inserts into the back corner here of your mandible. Questions here? All right. The other neck muscle we've got is the muscle that's going to allow you to do the oblique action of your head. When you squeeze, you go top right to lower left or vice versa, right? And this is your sternocleidomastoid muscle. The name of the muscle tells you what it's attached to. It's attached to the sternum. It's attached to the clavicle, clado. And it's attached to the mastoid process of your temporal bone. That's where we get the name. But in the end, that muscle is this. And when you pull it, it pulls you down into the side. Questions here? Sternocleidomastoid. It's a favorite. Because to spell it right, you need to have studied, and it's fun to say, and it's insanely easily recognizable. Right? So most people are asking this one. So, strategy. I will likely be asking that one, my kids. Major strategy. All right. Then we've got these powerful muscles of your humerus, right, to give you the push and the punching and the pulling that you need. And the push is the pectoralis major here. The reason why you have that flat body of the sternum is so we can attach this big muscle to at least some version of surface area and get us the strength that we need. The other thing we've got is your deltoid, your chicken dance muscle. This is hooked up here, and then it comes down to about the middle of your humerus and pulls that, and so this brings us up. Your deltoid will only allow you to get you up this far. If you do any time at the gym with shoulder exercise, you understand that that deltoid maneuver is up to this. It's not up to that, it's here. Why? Anything further, you're not doing deltoid. Anything north of that, you're working traps now, your trapezius in the back. And so we're getting you the chicken dance only to here with your deltoid. We've got a few different areas of it, but in the end is your shoulder muscle. So called because the Greek letter delta is a triangle, and this muscle looks like a triangle. Questions there? All right. Your trapezius is another geometrically named muscle, and this sucker looks like a trapezoid. It goes all the way up and attaches to your occipital bone of your skull. It comes down, attaches to your cervical vertebrae, and then continues to attach to every single thoracic vertebrae you have. And so this trapezius muscle really is most famous for giving football players no necks. And you're actually, if you've ever had a football practice, you grab on your face mask and you roll over the top of your helmet like this. You're strengthening those muscles so your neck doesn't get ripped off while you're playing the game. That's literally why people do that. It's not so they can look all big and tough. There's no aesthetic reason for this. It's functional only when you do that big traps thing. Call it trapezius because it looks like a trapezoid from your geometry class. Yes? Questions here? All right. Then you get your pulling muscle, your rowing muscle, your butterfly swimming muscle. You ever seen Michael Phelps? You ever seen Michael Phelps do this? And the guy looks like a freaking squirrel coming down in his tiny little waist and these massive wings coming off his back. And why? Because he's constantly pulling himself through the water with this action. Or if you're rowing, you're doing this. So whereas the pectoralis is pushing, your latissimus dorsi here is the pulling muscle. And is responsible for more of the triangular look of somebody who's really kind of muscular, right? That's that. It's pulling. Questions? All right. Then we've got your rectus abdominis. Rectus just means straight, right? And abdominis is your abdominals. Hooked up by an aponeurosis. This is going to take your xiphoid process and pull it closer to your pubis, right? So that's the general sit-up. But we've also got this motion. Oh, but wait, we've also got that motion. And oh my God, we've got that motion too. And so we've got the full circumduction going on around these very flexible lumbar vertebrae. But we understand that muscles can only squeeze in one direction. So how are we getting all of that play going on in this area? It's because your obliques here have 3 separate layers. We're asking you about the external oblique specifically. However, we've also got 2 other layers inside. And notice the grain of these particular stakes. One's going diagonal this way. What that does is when it pulls you that way. And only that way, the diagonal. Incidentally, that's why it's called oblique. Oblique means at an angle, yeah? All right. Then we've got another one going the exact opposite oblique angle, just inside. Well, when we don't want to go that way, but we want to go this way instead, we leave the outside muscle alone, we go to the middle muscle, because that's pulling the right way. And if I don't want to do any diagonal motion, I just want to spin, I go to the most inside, look at that grain, and now I do this, right? And so the way we get all this variation in motion is to stack muscles on top of each other, each orienting themselves a different direction and firing them off when necessary. Make sense? All right. Now down away from the torso and into your limbs. Your biceps brachii has two attachment points at the origin. That's why the biceps brachii, because what's this area of your body? It's the brachial region. You're not allowed to just call it biceps. Because while you have a biceps brachii here, you also have a biceps femoris back here in your hamstrings, and they're both biceps. And so you will not get full credit if you only say biceps, especially with the muscles. If there's many words you need to write out to give you the right answer, write them all down because they all are there for a reason. All right? We scientists are just as lazy as everybody else. We've just got a little bit more to keep track of, so we've got to add the complexity. But it's not complexity for no reason. So your biceps brachii gives you the flexion of your arm. On top of that, we've got the triceps brachii, which gives us the extension of the arm, the opposing muscle groups, right? Moving forward, moving down, you've got the brachioradialis, which goes from your brachial region down the radius. Brachioradialis, so it's the thumb side bone. If you've got anybody you know who likes to sit there and squeeze tennis balls or do the grip strength thing, this is where we're actually focusing on with that grip strength training, is the brachioradialis right there. These others, they have names, but in all cases, we're just going to call these guys the flexors of the forearm on the inside. Opposite side, the extensors of the forearm. Done with the arms and the upper. Questions there? All right, guys. So then we've got the legs. Gluteus maximus is your butt, and it's the largest muscle you've got. That's why it's maximus. From the gluteal region. As we get to the hamstrings down here, we can't call them hamstrings. What we've got is a biceps femoris, which is going to go lateral, and a semitendinosus, semimembranosus system that will go medial. And that's the only way to tell these different muscles apart, as far as I can tell, where they insert at the end. So they both are sitting up here on your ischium, and they come down, again, biceps femoris attaches at the knee lateral, semitendinosus attaches at the knee medial. This is one of the most common screw-ups on a practical, is those two muscles. And that's how you keep track of them. As we move to the front, we've got your crisscross applesauce muscle. That's called the sartorius. So called because a tailor is a sartor, and tailors crisscross applesauce in front of you to take the leg measurements for your pants. Yes? And so this is called the tailor's muscle. And this is the move you're doing with it. It's the one that comes from your ilium all the way down across the medial side of your knee. And that's why we can do the crossed leg thing with it. So that's a very obvious one. And that is this muscle here. I should have been pulling these models out the whole time. All right. From there, then, you've got your quads, your quadriceps. We're not going to call them quadriceps. You've got a rectus femoris that runs right down the middle and attaches directly to your patella, your kneecap. And then on either side, you've got the vastuses. And the vastus brothers are vastus lateralis and vastus medialis. And that's it. Together, quadriceps, because four heads all through them. Questions there? Don't call them the quadriceps. You won't get credit. Maybe in the gym, but not in our lab. And moving down now, we've got the gastrocnemius is your calf muscle. That hooks up to your calcaneal tendon to your heel, and when you squeeze that, you point your toes forward. That's it. For my class, you also need to know the soleus muscle underneath, a little bit deeper, doing the exact same motion. It's a stabilizer for that muscle. Up in front, you've got your shins. And your shin muscle, well, this muscle is right in front of the tibia. It is anterior to the tibia, which is where the name tibialis anterior comes from. Literally, it's telling you exactly where it is. It's not one you're allowed to screw up. So I usually put this one on my practical FIM simply because I'm trying to feel nice just then. Because, come on, man, do a little bit of effort. All right, with that, we're done with all these muscles. The rest of this just is a little bit more detail if we had time, which we do not, so I'm going to continue moving on. You guys keeping up? All right, 2 more labs to go. Nervous system and brain, right? Spine and brain. Neurons. Dendrites have ligand-gated channels. They produce graded potentials. Graded potentials, they're there as a means of bringing a signal into this neuron, right? Once all those graded potentials filter down to the axon hillock here, we see voltage-gated channels which can only open up by way of positives allowed in by the dendrite tree. And so down here, once we open up that first patch of voltage-gated channels at the axon hillock, which is right here, that's the decision-making site of the cell, then the rest of the voltage-gated channels that persist down the axon, they will automatically open up and keep that signal going as long as you're still built right, as long as you don't have multiple sclerosis or ALS are the most common interferences with that. But that's your general neuron. Dendrite tree, cell body for all the life stuff, axon hillock to make a decision is the first place in this flow of information you see voltage-gated channels, action potential all the way down to the axon terminal where it's going to spray neurotransmitter to the next cell. Questions here? Okay, keeping that simple. And that brings us to the nerves. And with these nerves, guys, it's just a matter of keeping track of the yellow lines, right? So this is your brachial plexus down here. And that brachial plexus is going to break out into 5 major nerves that we need you to know. The first is the axillary nerve. It's going to come through the muscle. It winds up being the first protrusion off your brachial plexus here. There are 3. The first one, axillary nerve, and all it does is it kind of gives you some sensation and some motor back here in your shoulder. It ends there. And your axial nerve, brachial plexus, axial nerve is going to be that guy. The next nerve to talk about is the last of those 3 cutoffs off the brachial plexus. That's your radial nerve. And again, it dives down into the meat of your arm, and then it shows up on the lateral side here. Radial nerve. That radial nerve will then continue around your elbow and down the radius side of your arm. That's where the term radial comes from. And so radius here. You need to be able to identify it there, there, and there. Any one of those places is fair game to ask the question. Next is your musculocutaneous nerve. There are 3 cutouts, or 3 little things, tabs, that come off this main body of your brachial plexus. First one, axillary. Last one is radial. The middle one is the musculocutaneous. Musculocutaneous, again, basically just comes out and dives out. On our models, we have no other place to show you the musculocutaneous. So in most cases, guess what nerve you're not going to be asked about because we don't have the ability to ask about it. Okay, so there you go. Strategy counts, yeah? All right. That's your brachial plexus. Now we get into the ulnar nerve, closest to the pinky side. That's it. It's over your ulna. We've got your radial nerve up top, and then we've got your median nerve in the middle. That median nerve can also be seen here on our torso model. I am once in a while evil enough to ask here what that nerve is. As we get down into the legs, and I don't have these nerves really to show you, I don't think, or maybe I do. No, these guys still have their muscles on them. All right, so what we've got here, your sacral plexus. Sacral plexus is the largest plexus you've got. A plexus is simply an ability to get the same information in the same spot over multiple roots. That way, if one of those roots gets blocked or injured, I can still move my body, right? So we've got the brachial plexus on top, we've got a cervical plexus, we've got a lumbar plexus, and we've got a sacral plexus. your sacral plexus, that one's going to be responsible for giving you your sciatic nerve. Your femoral nerve that you see on the other side here, that hooks up with your lumbar plexus. And that lumbar plexus basically comes in and gives you that line. That femoral nerve from your lumbar plexus, a little bit superior to the sacral plexus you can see here, that's going to split. It's going to continue to be the femoral nerve here, but it's also going to give you the saphenous nerve, which curves down and around through your vastus and rectus femoris. On the back side of this leg, that's that same sciatic nerve. So we get this started with the sacral plexus. It comes down the leg, and then it runs down the back of your leg. If you've ever known anybody with sciatica, or you have it yourself, it's a fairly common thing because this is the biggest nerve in your body, right? And it comes from the sacral plexus, runs all the way down the back of your leg, and it splits just superior to your knee. Turns into the fibular nerve and the tibial nerve. And that tibial nerve just keeps going straight right down your tibia. That's where the name comes from, yes? That fibular nerve is going to continue to go lateral all the way down deep inside your tissues here. And so we can also ask you, this nerve right there, also the fibular nerve. You would know that, or at least surmise it, because it's above the fibula. And so it's a decent guess. And listen, guys, if you are completely at a loss, just try to take a guess. Don't leave it blank. Put the area of the body it's in. Put the bone, the name of the bone that's next to it, if you know that. Because in many cases, that's going to be enough. Even though you didn't really know it, you just squeak through and at least have credit. All right, so never leave this stuff blank. Understand the naming schema that we've come up with here as a science, and understand that a lot of times you can just kind of wing it and just say where it is in the Latin, and you still got it right, even if you had no idea where the hell you're actually talking about. So no blanks on these things. I can't give you credit for no answer. I can maybe get you half points for a decent guess. All right, so that's that. We've got these models in the labs. I don't have them here to show you, but this is your lumbar plexus coming off the lumbar region of your body, and that femoral nerve that we saw in the previous diagram. This guy over here, this is your sacral plexus coming down, and that big thick nerve coming down there, that's your sciatic nerve that's going to run down the back of your femur. All right, now we get to the brain. What did I say? We would get out of here at about 20 after? I think we might be right. Okay, not bad. Your brain's surrounded by coverings. Those coverings are called mothers. When we talk about those mothers, really, it's a mater, not matter. One T, mater is German. And so the dura mater comes from the same root word where the term durable comes from, tough. Right? That dura mater is a very tough outer shell membrane around your brain and your spinal cord. Just south of that, we've got your spider mother, or the arachnoid mother. It's no name because this mother has actually set up a bunch of support struts that puts this membrane a little bit off the surface of your brain. And that allows cerebrospinal fluid to flow in between this membrane and the actual brain. And then, closest to the brain, we've got the gentle mother, or the pia mater. And the pia mater is a very delicate thing. Its job is to hold on to the blood vessels, make sure they're not getting sheared as they dive into the meat of your brain, right? And basically, it's just gloms right down onto the surface of the neurons that make up your brain. So those three mothers are collectively termed your meninges. And so, unless you have a series of paperwork and a really good reason why, all of us here have been vaccinated against meningitis. And that's because meningitis is one of the most infectious diseases we got. If somebody with meningitis walks into the other side of the room, we can count on at least 5 people going home with meningitis today. And a good chance of death for all of them, right? And so meningitis is a swelling of those meninges. And it's that risk of severe infection, severe death, which is why we require it for almost everybody who sits in our classrooms. Vaccinate. Just vaccinate. Don't be dumb. That was my public service announcement for the week. And if you're offended, please go vaccinate. All right. When you get your brain, we've separated this thing into several lobes. And there are gyri and sulci here. Gyri being the upticks, the crests of these waves, and sulci being the troughs of these waves. And some of these actually bear witness to a border between one area and the next. But when it comes down to your major areas of the brain, your frontal lobe is right up front. This is executive decisioning, planning. This is you getting to school in the morning and figuring out which clothes you're going to wear today. Decision making. Just at the back of your decision-making center is what we call the motor cortex. That's this red stripe. And it's a headband that goes from ear to ear here. In the frontal lobe still. Every voluntary motion that you've ever had and will ever have starts there. Moves up to the frontal lobe to associate stuff, and then out to your spinal cord so it can send a signal to the right muscles to get that job done. In the back, we've got a parietal lobe, that's the green, and the very first gyrus of your parietal lobe is where every skin sensation you've ever felt is felt. It's another headband, goes from ear to ear, and so when I tickle this part here, there is a very specific area of that place that's actually mapping out and letting me know that my arm's being tickled, right? And so that's your sensory cortex. It's going to feel your skin sensation, send it to your parietal lobe to actually interpret what I'm feeling. I got cold, I got tickly thing, okay, it's my dog. Right? And you'd understand it's a dog because the parietal lobe is there for perception of your senses. Your frontal lobe is there for planning of your motor movements. And that's why the motor is associated with the front and the sensory is associated with the parietal lobe. Those are the association areas that are intact. Occipital lobe, that's where you see. Your temporal lobe is memory and understanding and language. And we've got a couple special areas in there, Broca's area, Wernicke's area, for the production of speech and the understanding of speech, all in the temporal lobe. On your brains in the lab, there's this one sulcus that is, some genius came in a few years ago and labeled with a pen. That's your central sulcus, and it separates your frontal from your parietal lobes. It's the gyri in the front and the back of that central sulcus that are your motor and your sensory cortexes. We've also got a lateral sulcus right here, which separates parietal frontal from the temporal lobe underneath. No such clear division between these lobes and the occipital lobe. Down the center of your brain, separating the left and right, you've got a longitudinal fissure. Once we get into the deep inside of this sucker, we've basically covered this. Motor cortex to planning, sensory cortex to perception in the parietal lobe. And so this is a lot of extra stuff we're going to blow through just in the interest of time. Temporal lobe is for your hearing. And there are maps for pitch and rhythm and loudness in there. And it also gives you your recent short-term memory, all in the temporal lobe. With that temporal lobe is your olfactory association area. So on your cranial nerve 1, those olfactory bulbs, they're the ones that actually grab onto your smell sensation at first. They're not the ones telling you what it means. They're just bringing the information in. To understand that that is pizza that I smell, what you need to do is send all that information here by way of your olfactory nerve, there's your olfactory bulb, to your olfactory association area, which sits in your temporal lobe. Your occipital cortex is your primary visual association area, but just like everything else, your eyeball sees it. Its job is not to understand it. It's to bring the information in. Your occipital lobe's job is to bring the information in. Then from there, we bring that to an occipital association area, which is going to recognize the patterns, check them to the patterns we've already seen in our life, and identify what it is that we're actually looking at. So it's a multi-stage process understanding any of our senses, yes? And we have various areas of the brain to do that. In the ventral area of the brain, we've got a cerebellum, different in texture, different in color, different in function. The cerebellum's job is to smooth out your motions. So if you've ever seen a baby go from this to this, That's cerebellar training is what's going on there. And every single time they grab that bottle or get that thing they wanted, there's a dopamine reward, and that sets up a plan of action for your cerebellum to work. Your medulla is where you get, it's just basically your brainstem. This is your breath rate, your heart rate, your blood pressure. You don't live without your medulla. Right in front of that is your pons. The pons is in large part a superhighway, just information coming to and from your brain from the body, but we also have some respiratory rate control in your pons. Also in this basic region, your diencephalon, which is coming right up top of it. We don't show it to you. It's not something that you need to know, but this is the general area of the substantia nigra, which is where Parkinson's is sourced out and all of its symptomology as those substantia nigra neurons die from that disease. Here we see the pituitary. That pituitary hangs out on our brains about the same semester the genius marked up the central sulcus. Somebody stole all of our pituitaries and we haven't brought them back. So that ball is what's supposed to be hanging off of that hole at the bottom of those brains in the lab, right? That pituitary sits in that sella turcica of the sphenoid bone we talked about at the beginning of the day, yeah? Here is your optic nerve. It looks like an X because the eyeballs take in the information, sends it to the optic nerve, but the optic nerve, this side actually goes to that side, this side actually goes to that side, it forms an X. If you're into your circadian rhythms or your 24-hour clock, right at the top of that X is a patch of about 1,500 cells that sees the light with you. And if you have trouble falling asleep after you've been watching your phone all night long, it's this area of your brain that's giving you the problem. Because you saw that light coming in from your phone, those cells at the top of that X are not intelligent. They see light and think it's morning, and you're not sleeping anymore because your body is convinced it's morning now. So how do you do this? You turn your phone off 2 hours before and all your TVs and your things that are shining light in your eyes a couple of hours before you want to go to bed, and you don't get your brain thinking it's morning and sunrise, right? Or you can get the blue light filters for your phones, that night version, that night stuff, that's actually just pulls out a lot of the specific wavelengths of light that are going to cause that action. So if you're having trouble sleeping, try that out, right? Melatonin might work, which is coming from your pineal gland, which we'll get to in a moment. Here are your olfactory bulbs just above the cribriform plate that you're going to smell with. We've got the corpus callosum, which is going to wind up giving you your left-right collection. Here is your pituitary gland. Your pineal gland is right here that gives you melatonin and helps you sleep. Something you're going to want to do quite a bit of, or as much as you possibly can over the next few weeks as you do the grind necessary to get your A. And with that, guys, I have run out of time, which means I've run out of material. Any questions? All right, remember this was not a fully exhaustive list. See your lab instructor for that list. But otherwise, I wish you all the luck in the world, guys. I hope we all get A's. Enjoy your holiday.